So, can we continue?
Yes.
Okay, so I started to write here 2 steps of the proof. So we try to prove this theorem. So let E be just the spectral measure for A, and we call that M is our spectral measure for the operator A and the system phi arrow. So what does it mean? It means that when we take the complex measure Mij, yes, for this matrix measure, it's equal just to A phi j phi A. Why? Because by the definition, this spectral measure is defined like this. You remember it, I hope, that the definition was like this, that the term number Aj was obtained just by taking the scalar product of the spectral projection Aj of omega on phi j, this from the second place, and then we take the product, the scalar product with phi a. Yes? So, but this is by the definition of complex spectral measures, just A, no, we can say EA, but this is E for short, E phi j phi a. Yes, so this is true. So, when we take the function f from our space L calligraphic to sigma, so again by the definition, for each j, fj belongs to L2 on mjj, yes? And mjj by this above, what is this? mjj, this is just A phi j, which we denote for short by A phi j, which is the spectral measure for the vector, for A, and this is the vector phi j, yes? So, now it's good to recall again functional calculus rule that a vector x belongs to the domain of the measurable function of the operator, such as operator A, if and only if this function h belongs to the space L2 on this spectral measure. This is the real non-negative measure. Yes? So, together, what does it mean? Together it means that this condition that fj belongs to this, we can interpret that phi j belongs to the domain of fj of n. Yes. So it was just the first point of the assertion. So it's okay. So now we have this function f from our space L2 sigma calligraphic, and let us take the class f and let us compute the norm to the square of the norm. So using our special formula for this class, we know that we can compute it by the following formula using just the integrals over the complex measure so we take the sum over all a and j from 1 to d of the integrals on r f j f a conjugated with respect to the measure f m I j. Yes, and now we shall use our lemma tool. Yes, we shall use our lemma tool, and what we see. So fj will be f, fi will be g. Yes, and x and y will be x will be probably phi j, and this will be phi, y will be phi a. Yes, so when we use this, we see that this integral, what is this? This integral is just so okay, I will write this and we will see that this is true. It's just the sum and we take just so what is this? This is the density. This is this density. When you see, yes, when we use this, yes, that phi j belongs to the domain of fj of a, yes. So when we take here fj and fi conjugated, so we see that this is the density for such a measure when here we have fj and here we have fa, yes, here we have phi a and here phi j with respect to the measure just nij, yes. So and we just so when we compute the integral over a set from the density, what we obtain? We just obtain the measure, this measure, we obtain this measure of the set R, yes? So here we just can write that this is just the measure of R, but which measure? This is the measure A of f j of A of phi j on the first place, and here fi of A of phi I. Yes? So this is such a measure, such a complex measure of the whole set R. Yes? What does it mean? So just using the definition of such a measure, we can write that this is the sum and here we should just take A of R, yes, the projection of all R. What is this? The identity, yes, this is the identity, and acting on those two vectors, so Fj of A phi A, and on the second place Fi of A phi I, and scalar product. This is a scalar product in the space H. I don't write so this. So having this, we can, what we see, we just have 2 times the same, yes? We have the sum, the product of twice the same vector, so this is just the sum 1j from 1 to d, the sum fj a of phi j, and on the second time we can write this the same using I, yes, I equal from 1 to d fi of a phi I, but this is the same vector, and when you remember the definition of our linear transformation, W tilde, this is just W tilde of f. So this is just equal to the norm of W tilde of f squared. Okay? So, I forgot only to write m here, and we have proved number 2. And now, to obtain number 3 is just trivial, because when we have something with 0 norm, this is also 0. So it means that W of f is equal to 0, so it's properly defined. Yes, so it means that the definition was proper. So it finished the proof of this theorem, and now using this transformation W, we will define something what will be called the canonical spectral transformation for A and phi. So the only thing we should do is to extend those W onto the whole space. Yes, onto the whole space, from the dense space to the whole space. And this is almost a trivial step. So, maybe, okay, I will write it here. The next theorem let m be equal again to the spectral measure for A and the system phi arrow. So here we still do not need the cyclicity in this theorem. It will be shown. And our assertion is as follows. There exists exactly one operator U, which is bounded from L2 of M into H, satisfying any f from the space L2 sigma of M, U of the class of F, yes, this should be on the space, our Hilbert space, so it acts on classes, U on the class F is equal to this, what we knew, J from 1 to D, Fj of A by J, and the last part of the assertion, the above, it's better to close the window. The above unique U is an isometry from L2 of M into, not onto, still, into H. And it's almost nothing to prove this, so I should only say that it's the standard step when you want to extend the isometry, which was built first on the dense subset of the Banach space, even if Hilbert space is not important, to the whole Hilbert space. Yes, but of course, in this situation, we don't know that it's onto. Yes?
On L2 is not on L2 sigma.
It was, no, but on L2 sigma, it was, so L2 sigma was the domain of W, yes? And L2 sigma was dense. It was the dense subset. It was dense subset, yes? It was dense subset of, sometimes it's almost equal, but generally it's dense. It's dense, and so this is why we can extend this to the whole space. Yes? And this is a standard extension rule for isometries. So its extension to isometry is general property that well, everybody knows how to extend this, taking the Cauchy sequence and that. Even convergent sequences. Okay, so this is just the corollary from the previous theorem. Okay. And now having this theorem, this property, we will say that we call this U, the name for this U is the canonical spectral transformation CST for A and a system phi arrow. This is the name, just the name. And the notation for this, because it's okay, when we have fixed A and phi, we just have this this not unitary, but this isometry. This transformation, we will denote it by U A phi arrow. Yes, this is just this U above. Okay, and now we are ready to, almost ready to formulate the theorem, but there is still one thing which should be defined. You remember, I hope, that in the proof, in the formulation of the theorem for cyclic operators, polynomials were very important, yes? So our assertion was the polynomials are in some sense dense in the space and so on and so on. So here we also need polynomials, but the problem is that in what sense we can consider polynomials in such a space. Of course, we consider functions of on R, yes, because our spectral measure is on R, but we have values which are vector values, yes. So what kind of polynomials? And so we should define this. It would be vector polynomials. So on each term will just would be polynomial. So I will give some convenient notation for monomials first to obtain polynomials. Vector polynomials. So let us take n belonging to n0 and j equal to 1 to d, and by x with n above and j below, we shall denote the following function on R with values in R to the power d. What is this? This is just, we can say, the monomial x to the power n on the jth coordinate, yes? So, not coordinate, but on the jth place, and the rest would be 0. So, what does it mean? It means that this is just the function which can be defined like this. X to the power xnj is equal just to x to the power n. This is the scalar function, yes. This is, let me recall, x to the power j, n on t, where t is real, is just 2 to the power n, yes, by the definition, because this is the nth power of x, which is just t. So this is t to the power n, and so this is this function times the base vector in CD, which is equal to AE. So this is G, yes. G, this is 0 on the place G, this is 1, and the rest is 0. So this is the definition of such an element, of such a function. Yes, and now the set of all polynomials so we will denote by pole D of R. What is this? It means that it is just the that power of all polynomials is polynomials on R. Yes. So this is just the linear span of the set of all such functions, x to the power n, j, where n belongs to n0 and j is from 1 to d. Yes. And now, if we have a d by d matrix measure, if M is such d by d matrix measure on Borel sets of R, that all those polynomials, vector polynomials, are included in the space L2 calligraphic of M. It can happen that it's true or not, but if it happens, if it's the case, then we denote by pole from polynomial of M, we denote, of course, the set, the space of all classes of F, such that classes belongs to A2 of M, such that F belongs to this pole D of R. So this is just the notation, and of course we should ask the question, what is in our case? Yes, what is in our case? We just know what is our matrix measure. Yes, it is this matrix measure constructed for the operator, and we should take some cyclic operator, finitely cyclic operator, and cyclic phi arrow, and the question is, would this condition be satisfied? So we need the following lemma. I think I will not prove it, but it's not difficult. Lemma. Suppose that A is self-adjoint in H, and we have a system in H to the power D. If all the terms of the system F1 to the Fd to the phi d belongs to the space D to the domain of dA infinity, then this condition holds, and even more, the space of polynomials is even included in the space L2 sigma of M, which is very important for us. So it's quite easy to prove such a condition. I leave it, but it's you can say just an exercise from the spectral theory. And recall me that when we assume that the system is cyclic, this is one of the conditions for cyclicity. Yes, we should assume this to make sense, of course, the definition of cyclicity of this system. So, in our case, this will be satisfied. It's important. So now let me formulate the main theorem, which in some sense is almost proved by the previous steps. So it's only a problem to take everything together and to formulate. Okay. So I will try to formulate this theorem similar to the formulation of the cyclic case. So it will be quite long, but sometimes all these parts are important. Of course, the general assertion is that the finitely cyclic self-adjoint operator is unitary equivalent to the x to the multiplication by x in L2 space for the appropriate matrix measure. Yes, but we have something more. So I would like to write everything. So this is our main theorem. Theorem x multiplication unitary equivalence for finitely cyclic case. If A is self-adjoint and finitely cyclic in H, and phi arrow a cyclic system for A, M is the matrix spectral measure for A and phi arrow, and U is the canonical transformation for A and phi arrow, then point 1. Polynomials, also these D polynomials, we can say, are included in L2 sigma of M. We saw this, we have proved this just, and thus the polynomial subspace of L2M, yes, this polynomial space, the definition just disappeared, I'm sorry, but it was just the space of all the classes from this, yes, is dense, in R2 of M.
Prima melodie. Prima melodie.
And here,
Ah,
maybe here without D. Still without D, because D is in some sense here, yes, in M. Yes, is that, so this was the point first. As the second point is U is the unique operator, how to write this operator, from the set of all such U prime bounded being bounded from R2 of M into H, that for any N and J, for N and J, U prime on X Jn, this is this basic monomial, yes, that U prime of this is equal to A to the power N on phi J, yes, and the point 3. Point 3 is that U is a unitary transformation from L2 of M onto H, and the last, and the last point is that this transformation gives the unitary equivalence between multiplication and A. A is equal to U T X U to the power minus 1, where this Tx is the multiplication by x in our space L2 of M. So this is the end of the formulation, and now let us check what's going on, why it's true, yes? So I told you that we are almost ready, so the proof is just in the whole our investigations of today. So first was proved, yes, because we know that this condition is satisfied for the cyclic sequence, yes. So this lemma gives our the first part. Now, okay. Sorry. Yes, but this is only one part of one. Yes, and now we should prove that polynomials are dense. Yes, you should check this. What we know? We know, I should record this, that we know that when we take f in L2 sigma of m, then u of the class f is equal to the sum from B1 to D, Fj of A on phi j, yes? So, when we take f, which is just equal to this mononomial Fnj, so what we obtain? We can compute that u of this class. What is the situation? Here only the term number j is non-zero, the rest is zero, and this one non-zero is just x, is just the function x to the power n, yes? So what will we obtain from this? We have only the number, I'm sorry, this is the same, okay, so let's take here k, okay? So here only for j equal k, we have something which is non-zero, and we have just x to the power n function of a. So this is a to the power n of phi k, yes? So this is a to the power n on phi k, yes? Okay. What we know? We know that our u from the previous theorem, which you proved, we know that u is an isometry from the space L2 onto a subspace of H. But it's isometry, so the subspace should be a closed space, yes? And on the other hand, we know that it contains the orbit, which is linearly dense. So the image of U is dense and closed, so it's the whole space H, yes? So, okay, we now know that U is the unitary operator, yes? So we proved 3. Moreover, having this and knowing that the orbit was dense, was linearly dense, I'm sorry, and using that that U is a unitary transformation, we see that the set of all those mononomials is also linearly dense. And what does it mean? The linear span are just those pole of M. So polynomials are dense. So we proved the whole 1 and whole 3, yes? So now that this is the unique operator satisfying this, we know that our operator satisfies this, and this is unique because of this density and the continuity. So it's also proof. So we must only prove this last assertion and hope it's here when the proof of the situation with cyclic is just it's just the same with the proof of this finitely cyclic. So to prove this we use just the same arguments. I will not repeat this. I showed this argument on the first part of the lecture. So this is the end. So you see that it is technically maybe somewhat complicated, but it seems to me that it has some mathematical beauty. And and it's important. Yes, I will say something tomorrow on the seminar. I will show, maybe it's too much, but I will give an example where it can be an important tool. This property, this spectral, we can say this spectral. In some sense, this is a spectral resolution, kind of a spectral resolution for each finitely cyclic case. So it's all, for instance, it works for Bloch-Jacobi matrices. Well, thank you very much. I'm sorry that it was too long.
Very interesting. Questions? Comments? Are there some applications of such operators in mathematical physics?
You know, I am not the right person to answer such questions, because I am not a person which is good in mathematical physics. I'm just a mathematician, yes, and I like when sometimes I see some, maybe not applications, but some relations with physics. But here I can only say that I know that some Bloch-Jacobi matrices are sometimes used for some physical reasons, and I think that it should be important that you can find something like the spectral resolution for such a operator. But to tell you about something concrete, I'm not the right person. I'm sorry.
Well, some more questions?
На самом деле, it's nice to have program. Well, and you even use these techniques, this idea, these results.
So my main
You are a mathematician.
yes. So I told this that tomorrow on the seminar I will tell something about the subordination theory, which was quite important tool, mathematical tool, to check, for instance, absolute continuity of Jacobi matrices, scalar Jacobi matrices. And I hope that in some sense this kind of spectral resolution also for Bloch-Jacobi matrices will also help to find something similar, some similar way of proving, for instance, the absolute continuity of some Bloch-Jacobi operator. But this is only my hope now, not only mine, but also of my colleague. So tomorrow I will tell you something about this, but mainly I will tell about the scalar case, but I will also show what probably can generalize this for Bloch-Jacobi case, yes.
Thank you very much again.